So, welcome back. In this lecture, I will cover a different class of materials, and that is polymers. Now, polymers, they are essentially made up of carbon, hydrogen, oxygen, nitrogen, and it is an extremely versatile material because it is used not only for household applications, but also various engineering applications. So, I will first briefly introduce what are polymers, and then we will go through the different classes of polymers, as well as how to make polymeric materials, how to develop the how to use the different manufacturing technology to process and fabricate polymeric materials. So, what is polymer? The formal definition of polymer is that it is a large molecule or macromolecule composed of repeating structural units, and these repeating structural units are called monomer. Okay. So, all these individual unit is called monomer, and when these monomers they are clubbed up together or they are brought together, they form a macromolecular chain which is called as a polymer. So, the way the polymers are synthesized, so one of the terms is very important, is called degree of polymerization. So, degree of polymerization, it is nothing but number of monomer units which are attached to make the macromolecular structure. And what is the polymerization process? This polymerization is a specific process which combines small molecules known as monomers into covalently bonded chain. So, across the chain, these monomer units are joined together by covalent bonding, and during the polymerization process some chemical groups may be lost from each monomer. So, that is also important to know. And monomer is also known as a repeat unit, because this is essentially repeated in linearly to make the full polymer. So, what are the different classes of polymers? So, here what you see that this AAA, this is called, or BBB, this is called homopolymer. So, here the MER unit is A or MER unit is B. So, essentially the homopolymer are those polymers with identical bonding linkages to each monomer unit. What is copolymer? When two different type of MER units are joined or polymerized together to form a large chain structure where two different MER units are covalently bonded to each other, then we call copolymer. In most of the cases for engineering applications, it is often the copolymers which have received more attention than homopolymers. Okay. So, these are the two broad classification of polymers. I repeat, this is these two major classes of polymers are homopolymer and copolymer. Now, few minutes back I mentioned that polymers are essentially large macromolecular structure. The question is therefore, how large are those polymers? So, just to give you an idea, this is one of the large macromolecular structure you can see. So, it almost appears to you like a snake like morphology, like snake if it is squeezed and if they are hiding somewhere in the forest, they also have similar kind of structural configuration. So, this is a typical polymer chain. They can squeeze, they can unfold, they can fold, everything they can do simply because of the fact these polymeric chains are made up of the lighter atoms like carbon, hydrogen, oxygen, nitrogen, those kind of atoms. And for example, here you can see there is a 2000 ethylene units and it is a 200 MER, and therefore, molecular weight is only 5600. What is the molecular weight of the polymer? There is one is a number average molecular weight and there is a weight average molecular weight. So, number average molecular weight is essentially the total weight of the polymer molecules in a sample divided by the total number of polymer molecules in a sample. So, that is why it is called number average. And weight average molecular weight means it is essentially this MW is based on the fact the bigger molecule contains more of the total mass of the polymer than the smaller molecules. So, therefore, there is a need to define a different type of molecular weight, and that is why it is used as weight average. This is the formal definitions or mathematical expression to define what is Mn and what is Mw. What you see, Mn is nothing but sigma, that is summation of Ni Mi divided by sigma Ni. So, where Ni is the total number of so Ni is essentially number fractions of the molecules of mass Mi. What is the weight average molecular weight? Weight average molecular weight is essentially sigma Wi Mi divided by sigma Wi. Now, what is Wi? That is the weight fraction of molecules with molecular mass, weight fraction of the molecules of the molecular mass Mi. So, this you can write down as sigma Ni into Mi, because Wi is nothing but Ni Mi, right. So, if Wi is the weight fraction, it is nothing but Ni Mi. So, if you do these further simplifications, you get Mw is equal to sigma Ni Mi square divided by sigma Ni Mi. So, this is fairly easy to understand. One of the major parameters often in this in the polymer science or in the polymer engineering that the people use to distinguish two different classes of polymers is the polydispersity index. So, polydispersity index is known as PDI. So, they do not, many times certain polymers they do not mention Mn or Mw values, but they mention about the PDI, and PDI is typically defined as Mw by Mn. That means the ratio of the weight average molecular weight to number average molecular weight, it is what PDI essentially meant. So, this is an important plot. What you see here, this number of molecules which are plotted and along the y axis, and molecular weight is plotted along the x axis. And what you see here, that in this particular graph, your mean of the graph is essentially your number average molecular weight. So, that is Mn, and Mw is your weight average molecular weight, that is here, and their viscosity average molecular weight, that is M eta. So, it is very clear that Mn is typically greater than Mw. Okay. So, this is how the molecular weight distribution curve that looks like for a hypothetical polymer. Now, before I show you that how the friction and wear resistance of different polymers or polymer based composites, they are different from that of the metal matrix composites and other classes of materials. I thought it would be important for you to know what are the different ways you can make this polymer in the laboratory or in the industry. So, these are the different techniques that I have mentioned here. One is the compression molding for thermosets, powder injection molding, extrusion and transfer molding. So, what we can do, what I can do is next few minutes or so, I can go through some of the individual techniques for you to show that how different processing techniques are being applied here. This is one of the very useful slide. It does not give, it not only gives the idea of the manufacturing of polymers, but also it gives a broad idea that how different techniques, manufacturing techniques can be used for metals, ceramics and polymers. Now, if you follow this kind of thread, so you have a raw material, so it is a molten material. So, molten material based techniques are mostly used for the metals. So, it goes to castings and different shapes. It can go to conventional casting, it can go to the continuous casting or rolling. After it is rolled, then it goes through machining. Or if it goes to ingot casting, then it can be extruded, it can be forged, it can be rolled. and then after the extrusion again it will go to machining. After machining, all this finishing operation is to be done, then assembly, then products. Now, from the powder based techniques like for like metal powders or ceramic powders or polymeric powders, you can do injection molding, and from injection molding you can do firing or sintering, and then or you can do pressing and you can do firing and sintering. After that you can do finishing. So, these are the two different classes of routes. One is the route 1 I have mentioned, and one is the route 2. So, route 1 essentially is the molten material based route, and route 2 essentially based on powders. So, depending on what is the starting material, your manufacturing techniques can be quite different. One of the reason that metals are very popular, because all these techniques like welding, casting, rolling and machining, they are very much reproducible and they are very widely used in the metallurgical industry. Now, coming back to the different polymer processing techniques, for example, here I am showing you compression molding. Now, compression molding is used very widely in the polymer industry. So, it is a fairly simple techniques. The heart of the compression molding technique is that how you design the mold, because the designing of the mold is dictated by the fact that what would be your final shape and size of the polymeric products. So, you have a male and you have a female of this particular designing of the mold. Then one cavity you can pull it, you can fill it with the polymer powders, and then this particular top punch it can be lowered and then it can be pressed, and this is there is some pencil heater which is also attached to this platen. So, through this pencil heater you can locally heat this lower punch, lower part of the mold, and as a result by the application of heat and pressure this particular these polymers can be shaped into particular product. Another polymeric processing techniques which is also widely used is called extrusion of the polymers. Now, in this particular sketch what you see here, that you have a hopper here, right. So, this hopper or feeder essentially gives the input, right. So, this is your polymer powders or more than powders, it is the polymer bits and polymer granules which are taken into the extrusion chamber. And then what you see here, you have screws, and these screws threads have different geometry. So, the moment these polymer granules are fed into the extrusion chamber, and then screws that will push these polymeric things to this particular area, and this is the die orifice, and then extruded rods can be taken out from this end. So, this is your extruded rod of polymer. So, depending on what is the diameter of this die orifice, extruded rod has a specific diameter. Now, what happens in this reaction chamber? So, there is a feed zone. Feed zone is essentially where there is hopper or feeder essentially feeds the polymer granules into the reaction chamber. Because of the continuous screw action and friction in the screw and polymeric granule interface, that will locally heat. You can also have the specific heating station along the length of this reaction chamber. You can also insert certain thermocouple just to monitor the temperature of the polymeric fluid or polymeric melt as it goes through the reaction chamber. Finally, the melt temperature also is monitored by melt thermocouple. All this temperature monitoring is very important because polymer's viscosity is directly dependent on the temperature. So, therefore, there should be a very close monitoring of the polymeric the temperature of the melt. So, after the feed zone there is something called melt zone, and then third one is called melt and pumping zone. After the melt zone, these polymers getting pushed to melt and pumping zone, and then it finally goes through the die, and then you can get the extruded rod of the polymer. This is another way that this is the another very simplistic description of the compression molding, which I have shown you just 2 slides back. So, you have this polymeric charge, polymeric powders, then you place this upper mold in close contact with the lower mold half, then you take it out, then you get the molded part, ejection and removal of the part. Now, powder injection molding, that is also another technique which is commercially used. Now, injection molding is not only used for polymers, it also used for ceramic or ceramic based materials. So, this is the generic description. You have the feedstock, then you have the molding operations, then you have the debinding, and you have the consolidation. So, debinding essentially is to remove the binders from this feedstock after the molding is over, and consolidation is finally something to consolidate the material into a very dense structure or dense shape. Now, this is a schematic representation or process description of the debinding, and what you see here is that you have a powder. It can be ceramic powder or polymer powder, and it has a binder. First, it is premixed. The premixed powder with binder is charged into the mixing and pelletizer. Then it forms a pellet of different size. Then it is fed into the injection molding chamber, and then depending on the mold shape and size, you finally get this particular product, which can be further undergo debinding either by thermal debinding or pre-sintering or by sintering. So, this is that essentially the lower part of the earlier slide. So, you have a feed hopper where you can put the polymer granules or small pellets. Then the ram will be forced from one end to push the polymeric charged material to get into the mold. Now, if you have a mold cavity, depending on how many cavities you have with particular shape, this polymeric melt can be pushed into individual cavity by displacing these things in these particular directions, and then you can allow the melt to cool down, and then you can get the polymeric parts, injection molded parts at the end of the processing. Now, these are called what is called conventional manufacturing techniques of the polymer, but there are certain advanced manufacturing is also investigated in the lab scale, and some of them have also been used currently in the industrial scale production of the polymers, particularly for many of the biomedical applications like orthopedic applications. It is the selective laser sintering which is important, or electron beam melting is important, and microwave sintering is also another thing that is used for the uniform heating for the ceramic based materials. So, one of the techniques, advanced manufacturing techniques, which has particularly received wider attention is 3D printing. Now, 3D printing is also used for polymeric based materials. So, this particular slide provides you a very schematic representation about how 3D inkjet powder printing works, or what is the working principle of this particular additive manufacturing technique. What is additive manufacturing? This is a special class of manufacturing which involves layer by layer assembly of a particular product depending on what is the input design. So, if you look at this particular slide, if you look at this panel A here, so this is a binder depositor cartridge here, and this is your essentially build bed. Build bed is the bed where the product is kind of built up, and this is the feed bed. So, from feed bed, the powders are displaced and it has been sent to the build bed, and each layer by layer this build bed, this particular product is being built. Now, when this now if you look at this particular thing, that how it looks, you will see that this is the binder depositor cartridge, and there the heating element is there. So, in this heating element, it increases the temperature of the binder, then there is a bubble formation, there is a bubble burst, and this binder will be ejected from this surface. And this binder ejection, then it comes, and then it is essentially it will be falling on this particular powder bed, and this powder bed, this binder will interact, will penetrate into the powder bed, and there will be physicochemical interaction. So, some of the important parameters of the binder which are important, like pH, that is minus logarithmic hydrogen concentration of the binder solution, thermal conductivity, viscosity, surface tension, and so on. What are the important parameters for 3D powder printing? One is the process parameter, like what is the layer thickness in each case of this layer, and therefore, what is the binder saturation, deposition speed, build orientation. Build orientation means, suppose this is the one of the orientation of the build orientation can be minus 45 plus 45 also. So, there may be different type of build orientation. And what is the binder characteristics? I have already mentioned. What is the powder characteristics? What is the powder size distribution, particle shape, flowability, wettability with binders, and what is the post processing, like chemical conversion at high ambient temperature and high temperature heat treatment is equally important. Okay. So, what are the, just to show you that what is the importance of the different binders. One of the materials which is being printed using different phosphoric acid concentration, like 5% to 30% phosphoric acid concentration, you can see that at particular composition the strength increases, and then however after debinding, and however if you increase the higher concentration of phosphoric acid, strength again drops down. So, therefore, what these results indicate that 10% phosphoric acid binder concentration is the most suitable for the post processing. This is also another technique which is currently used for 3D plotting of the polymeric materials like alginate and so on. So, again like 3D printing, it also develops this total structure by layer deposition. However, here this starting material cannot be powder, starting material can be a paste, and that is why it is known as the manufacture of 3D scaffolds by displacing pasty biomaterials at ambient or physiological temperature. So, essentially it is very similar to fused deposition modeling, but here this material should be pasty and it is extruded in a standalone process. So, I think that the most of the manufacturing, the techniques that I have shown, that are quite useful not only for conventional manufacturing, but also for advanced manufacturing. So, summarize what we have learned from this particular lecture is a conventional manufacturing and advanced manufacturing, and conventional manufacturing is mostly based on molding of polymers. So, it can be either injection molding, compression molding, or it can be by extrusion. Okay. And one of the biggest advantage of the polymers processing with that of the with respect to the metals is that polymers have a very low processing temperature. Most of the polymers, they can be molded or extruded as low as 250 or 280 degrees Celsius, which is not the case for ceramics, or which is certainly not the case for metals. In case of ceramics, it requires very high sintering temperature, more than 1200 or 1400 degrees Celsius, and in case of metals like steels, normally steel melting takes place at 1600 degrees Celsius. So, therefore, these two polymers, that way it is advantageous because it does not require very high temperature. Advanced manufacturing, we have mostly learnt about the additive manufacturing technique, and additive manufacturing and AM actually is a more generic name, and some of the things that we learnt is 3D powder printing or 3D plotting, 3D PL. So, these are the two layer by layer fabrication technique which can be adapted very easily for polymers as well. Thank you.